Howdy, everyone. Today we're going to take a look at section 9.0, which is actually not a section you'll find in the book, but it is going to cover some review material that you may have picked up last year when you were in Algebra 1. And it's going to be some material that we're really going to want to make sure we have nailed down before we dive more deeply into chapter 9, I should say. So section 9.0 is an algebra section, and it is about using properties for radicals. So let's talk about the word radical for a little bit. So the radical refers to this symbol right here, which oftentimes is referred to as square root. That's the proper term. I know that when I talk to a lot of students in class, they refer to this as the square, and that's not quite true. And I'll talk to you a little bit more about how it is related to squares in a couple seconds. So let's see if we can take a look. The way that a square root works is that if you have a large number, like let's say 100, the square root works is by thinking about 100 by thinking to yourself, what number times itself will give you 100? And if you can figure out what is that mystery number that multiplies by itself to produce the value that you have, that would be the square root. So in this case right here, 10 times 10 is going to give you 100. So the square root of 100 is going to be equal to 10. Okay. So now let's talk about that other piece that I was mentioning, how some people refer to this as a square. Now, this is how it's going to work. This is going to be related to the idea of opposite operations. If you take a look at some of our basic operations right here, we're going to start off with addition. The opposite of addition is subtraction. The opposite of multiplication is division. And the opposite of a power of 2. This is a square right here. This is a square. The opposite of a power of 2 is your square root. So they are closely related to each other, but they are related to each other in the sense that they're complete opposites of one another. So it's a dramatic change between the two. So you need to make sure that you know the difference between a square, which is a power of 2, and a square root, which is a radical. So we got to make sure that we're thinking about those two pieces. With that in mind, though, the relationship between these is really, really important because you're going to want to remember some of your very best squares to help you find your square roots. So let's make a little list. These very best squares that I'm talking about are called the perfect squares. And so what I want to do is I want to talk about some of the values that you produce when you use powers of 2. Like, what about 1 squared? If you have 1 squared, that would be the same as 1 times 1, and that will give you a value of 1. If you have 2 squared, that will be 2 times 2, which would give you a value of 4. These are important numbers, and we're going to want to keep them in our mind today. 3 squared would be 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. 9 squared is 81. 10 squared is 100, as we already talked about. 11 squared is 121. And 12 squared is 144. Now, these are the first 12 perfect squares, and these are the most popular ones. When you go into Algebra 2 next year, they're going to want you to know these first 12 as well. So these are just things that hopefully you already kind of have in your brain already. And if not, then we're going to try to see if we can make them perfect this week. Okay, let's take a look at some of these other ones. So now what I have right here is I've got a couple of problems, and I want to see if I can simplify these. I want to see if I can take the square root of these numbers that I have right here. So 128 is the first value. So now my first idea would be, well, just like I had before, what is a number that multiplies by itself together to give you 128? Well, I can't think of one off the top of my head. If you remember, we jumped from 121 to 144, and 128 would be somewhere in the middle there. This was 11 squared, and this was 12 squared, so I can't think of a good one. If I try to use my calculator on this value right here, I'm going to get a very ugly decimal. Now, that's an accurate decimal, but it's not what I want. If we're going to try to write that down on the page, we're going to have to round it, and that's going to be inaccurate, so I prefer not to have a decimal. So I'm not going to choose that. So what are we going to do instead? Well, what we're going to do is we're going to try to break up this 128 a little bit. And the way that we're going to try to do that is we're going to try to see if we can think about which of these perfect squares from our list that we have already can we multiply by another number to give us a 128. And so you're going to want to try to start with some of these higher ones. Can you take a 144 and multiply it by something to get a 128? Probably not, because it's so big. Same thing with 121. 120 was super, super close. So to multiply it by something to create 128 is probably not going to work. So as you work your way back through the list, a good value that you're going to come across is 64. Specifically, 64 times 2 is the same as 128. And you can see that on my calculator right there. This is just a process of guessing and checking. It's not an accurate thing. You're just going to work it through the very best that you can. Some things that are nice are that the numbers are all even. There's no odd things or factors of 3 in here. So that's good kinds of things to keep in mind. Okay, so now that we've broken it down, why would we want to do this? Well, what we're going to do right here is now we're going to take each element that creates the 128. We're going to take the square root of those things. So now square root of 64 is fantastic. I already know that 8 times 8 is 64. Square root of 64 is 8. Square root of 2, not so much. 2 is not part of our perfect squares list. So that was one that, once again, you would create a decimal. So if you try to take the square root of 2, you're going to get that ugly decimal. Well, I still want to avoid those decimals. So I'm going to, and the way that I'm going to is I'm just going to kind of be lazy about my square root of 2. I can't really do much with it. So I'm just going to leave it alone like this. And this is going to be my very best final answer right here. 8 root 2 is the very simplest way I can write that. All right, your turn. See if you can try out the same kind of thing with 96. 96 is going to live somewhere between 100 and 81. So there's no perfect square just for 96. So see if you can come up with a couple of values that are in this perfect square list that will multiply together to give you 96. Values that I was thinking of were 16 and 6. And the reason why I would want to use 16 is because the square root for 16 is fantastic. It's going to be 4. Square root for 6 is not so great. There is no way to kind of get a 6. 6 is halfway between 4 and 9 right here. And we're not going to be able to do much with it. So 4 root 6 is about as nice as we can make it. And we're going to leave it like that. So those are your two most simplified versions. Are they great? Absolutely not. But they're much better than they were originally. And so we're happy about that. Okay, let's bump up the intensity a little bit. Instead of just looking at one square root, let's see if we can look at a couple. So multiplying square roots is going to be a big deal. We'll also talk about adding and subtracting them and a bunch of other different ways to combine them together. So let's see if we can take a look. So for our first set right here, we've got 2 square roots and we're multiplying them. So in general, the way that this works is when you're multiplying, you can multiply anything that is like. So if you have 2 terms that are both underneath a radical, you can multiply them. If you have 2 terms that are outside of a radical, you can multiply them. You cannot mix and match though. You cannot multiply something that is outside of a radical with something that is inside of a radical. That doesn't work. So we're going to just make sure that we're being consistent about it. So right here with our multiplication, both of these numbers are underneath the radical. So that means that you can multiply them. So we can change this to one big radical, and then we can put our 5s underneath it. 5 times 5 is going to give us the square root of 25. Now 25 is actually part of our list right here, and that means that it should be a nice square root right off the bat. Square root of 25 is, in fact, 5, because 5 times 5 is 25. Okay, so now this works out really, really nicely, and you get a very, very clean answer. And if you're being astute about things, you might notice that your answer is very, very closely related to what we had originally. We started off with a couple of 5s and we ended up with a 5. And that is not a coincidence. That is definitely how that works. What I'd like you to try to do in the future is we took quite a few steps to get there. What I'd like you to notice is that you've got this repeat customer showing up right here. And I'd like you to see if you can work your way to jumping from one piece to the other so that you don't have to go through this mental gymnastics every time you see this, because this is going to show up a lot of times. And so I want you to try to get fast at it. Will you be fast at it today? Maybe not. That's okay. But hopefully in the future, you can make the jump from here to here and feel confident about it without having to hesitate too much about that. Let's take a look at another one. So this other one, if you take a look, we've got some numbers that are simplified. They look a lot like the answers that we got from our last section. So now, once again, remember that when we're multiplying, you can multiply things that are outside of square roots. So we're going to multiply those pieces. And you can multiply things that are underneath square roots, but you cannot mix and match. So we are going to be doing some multiplication for both of these sets right here. So first of all, 4 times 5 is going to give us a value of 20. So we'll have that. And then our second set is going to be 3 times 2, and that's going to give you a value of 6. Now the 3 and the 2 were underneath the radical, so they're going to stay under the radical. Okay, so now once you've done that, it is important that you also try to remember that simplifying is definitely an important piece. So if you can simplify this at all, you should try to. So 6 is a number that is underneath the radical. If you can come up with some of the numbers from the perfect squares that will multiply together to give you 6, then you should do it. Now, 6 is going to live right here between the 4 and the 9. There's not a lot of stuff that we can use that is smaller that will multiply together to give us 6. And so this isn't going to do too much for us. This is about as nice as we can make it. We can't make it any nicer than this. All right, your turn. See if you can try this one out right here. You'll notice it's got a mix of both of the things we just talked about. If you're taking a look at our you try problem right here, you'll notice we've got a couple of values that are outside the square roots, which is our 4 and our 8. And we can multiply those. You also have these square roots of 13. There are 2 of them. 13 times 13 is 169. And not surprising, the square root of 169 is in fact 13. So our 32 stayed. And we now have a very nice 13 that is no longer underneath the radical. The last little piece about this is you can multiply these two pieces together, and that'll give you a value of 416. Once again, if you have two values that are outside the radical, you can multiply them. And this 13 is now outside the radical, so you can multiply it. Let's try another one that's very similar to that. Here's this guy right here. This has 7 root 2 squared. Okay, so now there's a couple of different ways to take care of this, but I'm going to do this probably the most old school way, and it's because I want you to be thorough. I don't want you to take too many shortcuts, because sometimes shortcuts can really burn you, especially when they have to do with powers. So in the most old school and most rigorous way, the way that a power of 2 works is by repeating things. And specifically, it's going to repeat whatever you have twice. So we're going to have a 7 root 2, and we're going to have another 7 root 2. And the reason that I do this is because I want it to go very similar to the ways that we've already done things. I want to take these values that are both outside the square roots, and I want to multiply them. And then I want to take the pieces that are both underneath the square root, and I want to multiply them. Now, at this point, we've done this a couple of times. And so hopefully, once again, you're starting to feel a little bit more confident. When you have a square root of 2 multiplied by another square root of 2, I want you to try to make that jump. So you can skip over some of this repeat work right here and get right to the final answer. Root 2 times root 2 is 2. And so we can get down to this pretty quickly and easily. And hopefully that'll help us get to our answer a little bit quicker as well. Now, there are a couple of other ways you can kind of deal with this. You can kind of take your 2, power of 2, and everybody in the pool gets a piece of cake. And so you can kind of give it to the 7 and give it to the 2, which is what you'll find with these 2 pieces right here. I'm not a huge fan of that, because that can lead to some problems further on down the line when you start to introduce addition and subtraction signs. So I like to do it this way right here. You can choose to do it a different way if you would like. Here's your U-try problem right there. This is very similar to what we had right up over here. For this U-try problem, I want you to notice that once again, you've got addition and subtraction, so it is slightly different. The major thing that is going to be different about addition and subtraction is that you're kind of going to FOIL this. So I'm going to take my 1 right here, and I'm going to multiply it by a 1. And then I'm going to take my 1 and I'm going to multiply it by this negative root 5. Now, I can't do 1 times 5. That's not going to work, because once again, the 5 is underneath the radical and the 1 is not. But what I can do is I can set the 2 pieces next to each other. So I'm going to do that right there. I can do the same thing right here. I'm going to take this root 5 and I'm going to kind of FOIL that one out, or distribute that one. 5 times 1 is going to give us 1 root 5. And then root 5 times root 5. This is the shortcut that I'm hoping that you're going to start to feel comfortable with. A root 5 times another root 5 is a 5. And that's going to be really fast and easy, or you can slow that down if you'd like. Now, this last one is negatives. Don't forget about your negative sign right there. Okay, let's take a look at what we've got. I've got this 1, and he's the only 1. And so I'm going to keep him. Now take a look right here. I have a negative 1 root 5, and I also have a positive 1 root 5. Those guys are actually the same with opposite signs, so we can cross those both out. And then lastly, I've got my negative 5 right here at the back. This problem is getting a lot simpler very, very quickly. My 1 and my negative 5 are going to produce a value of negative 4. And there's my answer for that one right there. All right, that is multiplication. Let's see if we talk about division for a little bit. So now if you take a look right here, what I've got is I've got division set up as a fraction. So this is actually 4 divided by the square root of 5. Now, one of the big things I want you to know about these is whenever you're dealing with a division problem with radicals is if you have a square root down in the denominator, that's a big no-no. You're not allowed to have square roots down in the denominator. So what we're going to do is we are going to rationalize it. This means that we're going to rewrite the fraction with the same types of components, and it is going to be equivalent to the same decimal value, but it just won't have a square root down in the denominator. That will be the big difference. Okay, so let's take a look at what we've got going on right here. So this was 4 root 5. If I take a 4 and I divide it by the square root of 5, I get this decimal. And as we've talked about the whole lesson, that decimal is unsatisfactory. It's accurate, but it's just not what I want. I don't want to have to round it and write it down that way. So what I want to do is I want to see if I can rewrite this as a fraction with a square root in the numerator. That's okay, but not a square root in the denominator. So how do you do this? Well, what we're going to do is we're going to multiply the numerator and the denominator by the same thing. This is called a special case of 1. And the thing that I'm going to multiply it by is this offensive square root that I have down here in the denominator. So the square root of 5 is going to multiply on the top and on the bottom. And you can think about this. What would you have if you took a square root of 5 and divided by a square root of 5? Well, you'd have the same thing as if you had 5 divided by 5, or 2 divided by 2, or 10 divided by 10, or 1 divided by 1. Taking a value and dividing it by itself is actually 1. So what we're really doing right here is we're multiplying by 1. So this isn't changing the fraction. It is going to maintain that same decimal value throughout the entire process. It's just going to look different. This is like when you go to see your aunts and uncles, or if you go to see the people who are working at your bank. They might call you by a different name, maybe using a Mr. or Mrs., or they might call you by a nickname or a family name, but you are still definitely the same person. You're just represented in a different kind of way. And that's what we have right here. In the numerator, 4 times the square root of 5 is 4 root 5. And so that's about as good as we can make it. Down here in the denominator, as we've done a couple of times, when you have these repeats right here, you can skip right to just writing that as 5. So now we have this new fraction, and it's got the same elements of 4s and 5s and square roots, but now the square root is in the numerator, and so that looks a little bit better. If I type this into my calculator, once again, I'm expecting it to maintain the exact same value. I don't want it to get any bigger or any smaller. And you can see that the decimal produced here is identical. And so this means that it just looks different, that it isn't actually a new number. And that's exactly what we want to do. We don't want to make a new number. We just want to make it look different. Let's do another one. Here's yours, 5 root 7. Our offensive character is the square root of 7, so we're going to multiply that on top and on bottom. Our numerator is going to have one number that is not under the square root and another number that is, so they're just going to sit next to each other. There's no 35s here. Down here in the denominator, root 7 times root 7 is just 7. Now, if you can reduce these fractions, specifically the 5 and the 7 right here, then you should, but we can't, and so we're stuck. And so we're just going to leave this guy as our final value right there. Let's kind of bump things up a little bit. Right down here, if you take a look, our numbers are a little bit larger, and so there's going to be a bit more involved. So it says sometimes there is a bit more work to simplify the denominator. What would you do first in these problems? So for these ones right here, the reason I asked this question, what would you do first for these problems, is because there's a lot of different choices that you could have. Some people are going to look at this and they're going to notice the radical right away, and they're going to say, I need to rationalize this. I need to move that radical up into the numerator, and they're going to attack that first. Other people are going to notice that the number is huge, and they're going to say, that number's too big. I need to simplify first. It doesn't really matter which order you do it. You can simplify and then rationalize, or you can rationalize and then simplify. It's really up to you, but you do need to make sure you do both pieces. So make sure that you're doing both. I'm going to choose to simplify first just because the numbers are large and I don't feel comfortable with that. So I'm thinking about 50. And once again, I want to think about it in terms of my perfect squares that we had talked about earlier. What are some numbers from our perfect squares that we can multiply together to create a 50? And the one that I'm thinking about is 25, specifically 25 times 2. So square root of 25 is pretty great. And so I can rewrite this problem. The numerator of 10 stays the same. My denominator now is going to be 5 root 2. Okay, in that vein of simplifying, you can continue to simplify. These numbers right here are both outside the square root, and they are both large. And so we can simplify those guys right here. 10 over 5 can reduce. Now, these numbers cannot reduce. This is a 2 that is underneath the radical, and that is a 2 that is not underneath the radical, so they're not the same. And so I'm not going to be able to reduce those. But what I am going to do is I'm going to rationalize them. So to rationalize, we once again have to multiply by that offensive character, that is square root that we don't like the location of. And so we're going to do that right now. In the numerator, once again, we have a 2 that is not underneath the square root and one that is, so we can't mix them. There will be no 4s. We'll just have 2 root 2. Down here in the denominator, we have the root 2 repeated twice. And so we're going to multiply those guys and take our shortcut. And once again, very similar to what we had done over here with our numbers that were outside the square root, you can do it again right here with these numbers that are outside the square root, and you can simplify those. 2 divided by 2 is 1. And so that means that the final answer for this guy would be 1 root 2, or simply root 2. Your turn. Try this one out right here. I started off with my simplifying again. 75 is going to be 25 times 3. And so I've got my 5 root 3 right there. Now, if you take a look, I have this 5 over 5, and I could reduce it, and that would be totally fine, but I've chosen to rationalize first just to show you some variety. And so when I've done this, I've got my 5 root 3, and then I've got another 5 and a 3. There's no square root on that. That's just a regular 3. Sorry about my handwriting. Then what I'm going to do is I'm going to multiply 3 times 5 right here, and I'm going to get a denominator of 15. There's no square root down there in the denominator, and that's great. Okay, so now my last piece is we should simplify. 5 divided by 15 can reduce, and that's going to reduce down to 1 over 3. So our final answer is going to maintain the square root of 3 from the numerator, and that new 3 that we got from the 15 in the denominator. Root 3 over 3 is our final version. And for our last little piece right here, this is a little bit different. You'll notice we still have square roots down in the denominator, and that's still not okay. Our numbers are pretty small, so that's good. The big difference here, though, is that we have addition or we have subtraction happening down here in the denominator. And because of that, we're going to need to spend a little bit more time with them. Unfortunately, what you'll learn as you go through mathematics is that addition and subtraction is a bit strict and rigorous, and because of that, it causes you to spend a little bit more time with it. And so that is exactly what's going to happen here. It doesn't mix so well with the radicals and the division and everything else that's going on right here, and so we're going to spend some time. In order to get rid of this square root that's down in the denominator of this fraction, I'm going to need to really work it very carefully in order to make sure that my special case of 1 that I'm multiplying by is going to produce the results that I want. If I just take this guy and I multiply it by the square root of 5 down here in the denominator, I'm going to do 1 times the square root of 5, which is going to give me a square root. And I'll also do root 5 times root 5, which will give me a nice 5. So I'll get 1 really nice part and then 1 terrible part. So you can't just multiply by the offensive character right there. It's not going to work out the way you'd like it to. We will use the square root of 5, that's for sure, but he can't be by himself. So then the next logical thing is, okay, if 5 isn't good, let's use the 1 and the 5 because they're both part of the denominator. And that's a great idea as well. 1 times 1 will give you 1, which is pretty nice. And root 5 times root 5 will give you 5, which is pretty nice. But then once again, 1 times root 5 is going to create a radical, and so is root 5 times 1. That's also going to create a radical. So then we need a way to cancel these out, and the way that we're going to do that is by using a sign change. Now this is really just called the conjugate. So I want you to try to keep that in mind whenever you're working with any of these addition and subtraction problems. This conjugate means that you're going to change the sign specifically between our nice normal integer term and our radical term right here. So we're going to change that guy right in the middle between those guys. So that is going to change from addition to subtraction. And if it was already subtraction, it would change to addition. So it's not always going to be a minus here. It's just going to be a flip-flop or an opposite, just like we had talked about at the very beginning of the lesson. Okay, so let's try it out. So when we're doing this in the numerator, we are going to be distributing that 6 to both of those terms. 6 times 1 is 6, and 6 times negative root 5. Once again, you have a value that is not under the radical, and then you have another value that is under the radical, and they don't mix, so we won't have any 30s. Now down here in the denominator, this is going to be a little bit lengthy. So we're going to do 1 times 1, which is 1. That's great. We're also going to do 1 times negative root 5, which is going to be negative 1 root 5. Then we're going to do root 5 times 1. This is going to be positive values. That's going to be positive 1 root 5. And then we're going to do root 5 times root 5, which is going to be 5. That's our shortcut right there. Now remember that this root 5 was negative, so will our 5 be. Okay, let's simplify a little bit. Up here in the numerator, not a lot of simplifying to do, so we'll pretty much leave it exactly how it was. And in the denominator, what I notice is that I've got this negative 1 root 5 and a positive 1 root 5. They're identical in size, but they are different in sign. And so they are going to cancel each other out. So the only things we have left right here is going to be a positive 1 and a negative 5. That gives us a denominator of negative 4. Now for our last piece right here, the thing that I want you to try to do is, once again, simplify. If you've got some numbers that seem a little bit large, you can simplify them. In this case, what I want you to do is I want you to realize that you have got some numbers that are all outside of the radical, and you need to try and do your very best to find a good common factor for all of them. So these 6s and this 4. So we're using every number that is outside the radical, not the 5 because he's underneath the radical. A good common factor for 6s and 4s is 2. So we're going to pull out a common factor of 2. That common factor of 2 is going to give us an answer of 3 minus 3 root 5 over negative 2. That looks pretty great. Another thing that can occur sometimes is Sometimes the signs can kind of change their location. So right now I have a negative down here in my denominator, and there's nothing wrong with that in my personal opinion, but sometimes on standardized tests and in multiple choice options, you might not end up with the negative in the denominator. And so what sometimes they will do is they'll take that negative out of the denominator and they'll give it to all of the terms in the numerator. So that means that this 3 would become a -3, and that -3 would become a +3. And I just want you to be flexible enough to identify that this and this are the same. If you give me this answer, I don't really have a big problem with that. But I also want you to notice that if you're looking at a multiple choice set of answers and you see this one, that this is very much the same as that. If one sign changes, they all change. So we used to have positives and negatives and another negative, and now we have negatives and positives and another positive. So everything kind of changed, and that's still going to make it equivalent. All right, your turn. This is your very last one. To begin with, we're going to start off with our conjugate, which is going to be 3 plus root 2, which is the opposite of the 3 minus root 2 we had in the denominator. We're going to distribute that 7 to both the 3 and the root 2, which gives us 21 plus 7 root 2. Down here in the denominator, 3 times 3 is 9. And then you're going to have your 3 times root 2 and your negative root 2 times 3, and those will cancel out. So I didn't even write them down. This is my second shortcut that I want you to try to get comfortable with. You also have your root 2 times root 2 right here, and root 2 times root 2 is just going to give you 2. One of those root 2's was negative, so is our 2. All right, so then that means that once I do my subtraction, I'm going to end up with a 7 right down here. I also already had a 7 in the numerator, and I had a 21 in the numerator, and all of these guys have some good common factors of 7. So we're going to reduce them by a common factor of 7, and that gets us down to this guy right here. There are lots of 1s that you really don't need, and so we can simplify our answer to 3 root 2. Okay, that's everything that you need for section 9.0. Time to start working on the homework assignment. We'll spend some more time using the same kinds of ideas when we move on to section 9.1.